Okay. Okay. Hello, everybody. This is Professor Ma, and this is the summaries on these sections on the continuous and differentiable functions. So here's the list of what we um, call elementary functions. And basically, if we look at it, it's basically there's only three classes. They may have these algebraic ones, then you have exponential and log one, then you have all these trig ones, right? And these functions behave nicely. In elementary functions are function obtained by adding, subtracting, multiplying these functions and compositions, looping one into another. Okay, and the consequence of that is elementary functions are continuous in the domain. Wherever they define, they are continuous. Okay? They're not differentiable. We will see later. But then a word about the elementary functions. There's some discussion about exactly which class of functions should be included elementary function besides those. So there's some arguments. So if you want to see the discussion, you can Google it. Okay. So the takeaway from now is that all the elementary functions made up of those formulas are continuous. Okay, as long as it's defined at a point, it is continuous at that point. Sometimes if it's a boundary point, it's right continuous or left continuous. Okay. But, so what's the important things about the continuous functions? Well, the first thing important thing about continuous function is the intermediate value theorems. It says the following things. If I have a function defined on a closed interval from one end to the other, from A to B, and suppose let's suppose the FB is bigger than F of A. Then the intermediate value, it means any value in between FA and FB. Let me call it C. Okay, you take any M. Okay, take any intermediate value M. That intermediate value says that you can find some number C between A and B that which the value at C is equal to the M. This is actually classified if you think about it, it's actually classified what it means by I draw a point, a curve, it's continuous one point to another point. That basically I pass through everything in between them, quote unquote, in between on the coordinate system. Okay. Another things I want to point out is that there might be other C, okay? And the theorem just guarantees us at least one C. And so the phrase in mathematics, at least one C means that there's one at least, but that there might be a lot of others. Here's some remark about the theorems, and if the left end is bigger than the right end, instead of going up and the things it's bigger coming down like that, and then the statement can be phrased in these manners. And in particular, if the two endpoints greater than or equal to some strict, and then the point C might be one of the endpoints. Okay, these are just little details you have to think about. Okay, try to picture what it meant with the inequality strict or with the inequality with equal sign. Important theorems about these you can conclude from here. One of the theorem is, which is kind of obvious, we do try to draw it, is basically it says this: if I have a continuous functions, I tell you the function value at one point, at some point, say A, f of A is negative, okay, it's down below, and some other points at B somewhere over here, B f of B is, this is positive, is above, and then this function must have a root. That is, no matter how you go, it gotta cross somewhere. Okay, and that point crossing at the x-axis is the root. Okay, so there exists a C in between where FC is 0 if the signs are different. So, for example, this basically gives an argument that any odd degree polynomial, like over here, degree 3, must have at least one root. Why? Because if I'm plugging a large positive numbers in odd degree, like over here, cube, I'm plugging in 5, okay, and it will be positive. You can easily establish that. But on the other hand, if I'm plugging a very large negative numbers, like minus 5 or minus 100, then it's going to be, the output is going to be negative. So the graph must travel from the negative points to the positive points on top. So somewhere along the line, it must cross the x-axis. And that would be where the root is. Okay, so in particular, I can tell in these problems, this example, there's a root between 2 and 5. What? Because if I plug in 2, I can check it's going to be negative, and 5 is going to be positive. So it's somewhere around the line, along the line, there's a root. So in particular, if I want to graph these things, I want to look at the interesting pathway where the root is. I'll graph on the, on the software domain 2 to 5. Okay. So small things like that. But geometrically, this is obvious. The other things that are important about continuous function is a continuous function, again, closed interval, including the two endpoints, is that you must have a maximum and minimum inter-interval. Okay. And in particular, everybody in the formulas, I mean, everybody in the domains, the f of x, in the interval, the value will be between the maximum and minimum. So suppose this is the curve, and it's continuous from one end to the other. Then here's a minimum, and here's a maximum point over here, and then everybody's going to be in between these two values, and big M and little m. Okay, so in this stretch of value, so this will be where f of x is all going to be in here. In particular, this we use the phrase, we say f of x is bounded. So one more time, if I have a closed interval and f of x is elementary function, hence continuous, defined on the closed interval, then the theorem guarantees says there is a maximum and there's a minimum within the interval AB. So this is the existing theorems for elementary functions. Now let's take a look at differentiable functions. And differential functions is a derivative exists. Okay, and the first things is that differentiability is a last stronger condition. What we mean by that is you need a lot more things to satisfy a point. A function is differentiable at a point. Okay, continuous means it passed through without, not broken, but being differentiable, it means not only not broken, it has to be nice and smooth. You can take the derivative at that point. Okay. In particular, it means that rate of change can be measured. So at a maximum, extrema, maximum, minimum, the rate of change couldn't be positive because at the top, you're not climbing, you're not increasing anymore. So the derivative cannot be positive. On the other hand, you are not going downhill, so the derivative cannot be negative. So at extreme of the derivative, since it's differentiable, it has to be 0. Okay, so again, this is, we've seen that many times. Okay, and this gives us the Rolle's theorems, okay, which states this. Suppose I have differentiable function defined between on the closed interval a b, and the two endpoints are the same value, like this curve. Since it's differentiable, hence there must be maximal and minimum. Okay, so there must exist points where the derivative is zero. Okay, so if the endpoints are at the same level of a smooth curve, and then there will be points where derivative will be zero. Okay, let's see the pronoun C. The condition is that it must be differentiable. What happens if I don't have differentiable? Well, I could have a function that like this, with a point to come to a corner that's not differentiable. Okay, so but this refers to differentiable functions. Hence, we can take derivative and try to find where the max and min are. Okay, and here's a proof, and I'll let you read it. Okay, and then we're going to take these row theorems, we're going to tilt it, and that gives up something called intermediate value theorems. Sorry, mean value theorems. Intermediate was the other one we just talked about. The mean value theorems. Okay, but to talk about mean value theorems, first let's talk about this chord connecting from point A to point B. Okay, and the slope of the chord, which is this formula. Okay, so we call this value the average rate. Okay, the average rate of change between A and B. Okay. So if I take the row theorems and I rotate it a little bit, the picture now looks like the one on the right hand side. Then the statement, instead of saying that in the row theorems, then the statement is g prime of a point C has to be zero, has to be flat, okay, because it is parallel to the chord connecting A and B. But if I rotate it, then the slope of this, it is the average rate of change, okay, between A and B, A to B. Then you can find a point C where f prime of C is equal to this average rate of change. The same slope, because they're parallel. And that's the statement of the mean value theorem. So here, let me put into a complete statement. So we have a differentiable functions, okay, over A, B. So we have a function that therefore crosses A and B. That's differentiable. And if I were to calculate the average rate of change between this chord, the slope of this chord, then you can find a point C where the derivative of C, which is parallel to this line. In other words, the point of C is equal to these different quotients of endpoints. Okay, it has to be differentiable. This is something which continuous is not sufficient. You might have a pinch point. So this is called the mean value theorems. What we call a mean values over here, the mean in statistics, the word mean, it means the average. Okay, over here the average means the average rate of change. Okay, not slightly different from the average in a set of data. So this is the mean refers to the average rate of change between A and B. Okay, and then there's later on was something called the average value of the entire function, slightly different later. So this over here the average rate of change from A to B. Okay. And here is an interesting interpretation of what that meant. Okay, suppose you drive from Los Angeles to San Francisco and leave at 12 o'clock and get there at 3:30. Okay, and suppose the distance 350 miles. So I can calculate the average rate. The average rate of driving 100 miles an hour or flying, whatever. Okay, and what does that mean? Well, it means somewhere at a time, that here the parameter t is the time, somewhere at around 12 to 3:30, you looked at your speedometer, it must be pointing at 100 exactly. There must be some time. Okay, think about it. You couldn't be driving 100 miles, more than 100 miles all the way. You couldn't be driving less than 100 miles because then you wouldn't make it. So sometime your speedometer must be pointing at 100. Okay. Kind of obvious. Yeah. But what are kind of exercise we can use, we ask about this type of theorems, and there really isn't much. Okay, so the other type of exercise is exercise B, will actually ask you to calculate, find out where this value C is with parallel slope. Where is this value C exactly? And this is what example B is. Okay, so example B says, okay, here's a function from 0 to 4, and calculate where C is, and use the software to find out, okay, and justify your answer. Actually, what I'm going to do now is I'm going to draw the picture and kind of talk about the pictures and at which point you're going to look for, and that's on next few slides calculation. It's kind of obvious. I mean, it's really easy. Okay, so from 0 to 4, let me graph these functions, the square root functions. The when x is 0, we get 1. X gets bigger, it gets bigger and bigger. So basically it goes like that, right? Okay, so okay, again, it starts at 0, 1. When it gets 4, it gets up to the point 4 is 3, right? And basically we are trying to find, find the slope of the thing. What's the slope of the thing? Actually, we can calculate. So 3 minus 1 is 2, 4 minus 0 is 1/2. Okay, slope is 1/2. And then the question is asking you, find the locations where the tangent line where f prime of c is equal to 1/2. Okay, find these. And basically, pictures, that's what it's asking you to look for. And the calculation is straightforward. Derivative set equal to 1/2. Okay, and that's it. Okay, bye-bye. Till next time.